Hello and welcome. In this video, we are going to go over some features of psychrometric devices, test steps that can solve, analyze psychrometric processes. This is covered in chapter 12. You have to have a thorough knowledge of the moist air model, and we'll also talk about mass and energy equations and how to use them for simple heating, simple cooling, and different other psychrometric processes. Well, before going over psychrometric process devices, it's advisable that you have a good understanding of how to analyze any open steady device using suitable test steps. Well, the basic concepts, the animations, tons of animation in chapter 12. You'll find the basic concepts of different what properties of saturated air, etc., are developed. In manual solution, we use the psychrometric chart, which puts together a whole bunch of properties for a given for a given total pressure. So this chart is only valid for, say, this particular chart could be for 100 kilopascal total pressure. If we now if you go over a few psychrometric processes in simple heating, moisture is being heated, and as you can see, temperature is increasing and relative humidity is decreasing, while omega, the specific humidity, remains constant. So different processes, like you can browse through. This is simple cooling, cooling and dehumidification. Maybe we'll try to solve a problem like that, where a moisture is coming in, heat is removed, and we'd like to know how much condensate is coming out and how much is the heat transfer required given a state 1 and a desired state 2. Here is the energy and mass equation developed for a psychrometric, a very general psychrometric device where there is all kind of different things going on. So for instance, the mass for dry air is very simple. Dry air mass doesn't change, whereas the energy equation can be quite complicated because energy is brought in by moist air, energy could be added by water injection, energy could be added by steam injection, lost due to heat transfer, etc. Okay, so let's go and start the suitable psychrometric test step to solve a dehumidification problem. First of all, if we are just interested in a flow or system state, we can go there and open up the MA model, that's the moist air model, to find properties. But to solve a system problem, we'll follow the system analysis open branch, specific branch, and here is the HVAC psychrometric test step. There are a few video problems already solved here. So I'll just quickly go and set up an arbitrary problem to show how easy it is to solve psychrometric problem using this test step. Yes, there are a bunch of properties shown here, which requires further knowledge of moist air model, but essentially the total pressure is set to 100 kPa, about 100 kPa. So suppose hot and humid air is coming and we want to, a lot of it, let's say 100 meter cube per minute, and we want to cool it down, and it's coming at very hot temperature, let's say 40 degrees Celsius and 90% relative humidity, a terrible condition of air. And we want to cool it down to, let's say, 10 degrees Celsius. Of course, mass flow rate of dry air is not going to change, but when you cool it down, there's a good chance that water vapor will be condensing. In that case, relative humidity will be 100% at the exit, saturated air. So notice that the vapor flow rate is 0.8 kg per minute, whereas in state 1 it's 4.6 kg per minute. So obviously a lot of vapor must have condensed out to satisfy state 2. So to capture that, state 3 we'll say is the exit of condensate. So we pick the H2O PC model, so you can see the properties kind of adjusted to new model. So the water condensate temperature should be the same as the exit temperature of the air. That's the standard in psychrometry, and we'll assume saturated water, um, and that produces the state of H2O, except we want to find what is m dot 3. It's obvious it should be m dot of vapor at the difference between state 2 and 3, state 2 and 1. But if you go to the device panel, let the device panel do the job for us. Again, the mass and energy equation are shown here. Mass equation is divided into dry air mass and water vapor mass. And this is our device. So let's load the states that we know. It allows two different states to come, two different flow to come in. State 1 is our inlet state, moist air, as you can see, coming in. And we leave this particular inlet blocked because we have only one inlet through each state moisture is coming in. And let's say through state 2, moisture is going out, and state 3 is our H2O, the condensate going out. And also there is no external work, there is no electricity or shaft work. And now if you do a calculate, notice the heat transfer is found, so many kilowatt, and ton of refrigeration is used a lot in psychrometry. So it's a 58-ton refrigeration system that we need for this cooling. If you go to the state panel, you can find that mass flow rate at state 3 of condensate has been found in kg per minute is 3.78 kg per minute. So basically we have just defined a problem, solved it, and obviously you can do any number of parametric study by changing a variable and clicking the super calculate button.